Okay, so we already uh, learned how to use the maximum shear stress theory and the distortional energy theory and the Moore circle to evaluate the failure from the static loading, right? So now we're just gonna process to the next chapter that we are gonna focus on the component failure due to the cyclic loading. That's mean the fatigue. Okay, that's mean the fatigue. Therefore, for, therefore for the fatigue issue, we're gonna begin with the crack. I mean the fatigue generated from the crack and the crack propagation. Okay, and why the crack will propagate? Why? And what's those vectors to influences the crack propagation? So this the focus of this chapter we're going to focus on. Okay, so there's the example right here. So suppose we have a design with a ellipse notch here with the specific dimension A and B, right? When we apply the force and the stress, right? So from your the common sense, so you can tell me where is the stress should be concentrated. Which part of this component should have the highest stress concentrated? Right here, right? So I mean, the stress should be highly concentrated at this notch tip, right? This notch tip, right? So when this radius of this notch R approach to zero, that's mean the KT, which is defined as the stress concentration vector. Okay, stress concentration vector approaches to infinity. Approach to the infinity. Okay, approach to the infinity. And the stress will concentrate at that tip to reach the infinity. Okay, okay. And this criteria space can be applied to the relative brittle material. Okay, relative brittle material. So for most of the metals, we can regard it as the ductile material. However, under specific circumstances, like the low temperature, or this material has been um, strength hardening. So this ductile material will transfer to the brittle. Okay, transfer to brittle, especially for the temperature. Okay, therefore say the ductile to brittle transition temperature as the key factor for the fracture failure of metal. Okay, of metal. Okay, so suppose we have this geometry A and B of the ellipse notch. Okay, and if we look somewhere, the infinitesimal element somewhere here, we have this stress sigma y. Okay, so this maximum stress depends on the geometry of this notch and the applied stress. Okay, this equation is from experiment, therefore it's experimental equation. Okay, therefore when this notch B, the dimension of this notch B approach to zero, that's mean this term approaches to infinity. That's mean the stress will reach the highest, right? The stress will reach the highest. Okay. And then we define this term as the KT vector, named as the stress concentration vector due to notch. And this notch causes the crack and then propagates, and then propagates. Okay, basically there are three modes for crack. Okay, so the first mode, or we say this mode one, and this is mode two for sliding, and mode three for tears. Okay, for tear. Okay, so the most commonly used is mode one. Okay, it's mode one. Okay, so the following sections we're gonna discuss only on the mode one. Okay, only on mode one. Okay, so when this components have the notch, and we can evaluate the stress within this infinitesimal element. Okay, suppose we have this infinitesimal element right here, or right here, or right here. Okay, so its stress is sigma x, sigma y, and tau xy will be in this mathematic form. Okay, I'm gonna skip this derivation process. Okay, so well, I just want to tell you the three stress components around the crack tip. Okay, or around the notch tip. Okay, so the R represents the distance from the notch tip to that element. Okay, and the theta represents the angle uh, uh, between the small element and the x-axis. Okay. Okay, suppose when the theta here equals to 0, what we get? When the theta equals to 0, sine theta equals to 0, cosine theta equals to 1, right? Therefore, what we get? We get the sigma y or sigma x equals to the applied stress times the square root of the A. The A is a dimension, a half length of the crack over 2R, 2R, right? And when this R approach to 0, that means there's no radius, almost very small radius. And this sigma Y, the stress, will approach to infinity. Okay, will approach to infinity. Okay, therefore we can remove this part, this square root of the 2R, right? The square root of the 2R. We can rearrange it to the left side, right? So we got this equation. Okay, and this sigma is the applied stress, right? This the applied stress. We already know it, right? Okay, and A is the half crack length, half length of the crack right here. Therefore, this will be a constant, right? This will be a constant. Okay, when the R approaches 0, what's that mean? What's that mean? That means this small element, when the R approach to 0, that means the small element is really close to the crack tip right here. Okay, really close to the crack tip. So if the element close to the crack tip, that means R approaches 0, and this term will equals to a constant. Okay, we're equals to a constant. Okay. Okay, so this is what we write there. So this term equals a constant when this infinitesimal element approach to the crack tip. Approach to the crack tip. And then we define this constant is the factor or the parameter called the Ki or the K1. The 1 represents that I already mentioned previously, the mode 1 for crack. The mode 1 for crack. Okay, and the Ki is not the same as the KT. KT is the stress concentration vector due to the notch or the fillet, right? From your design, okay, from your design. Or the KTS. KTS the shear stress concentration vector. Okay. And the KI or K1 is defined as the stress intensity vector. Okay, so commonly used, we could say the KT for notch or for the fillet that you design, right? Because you are an engineer, you design the notch or you design the groove, you design the key lock and so on. And the KI is being used for the crack. That's mean we observe the metal or the components inside the component. We can observe by the some SEM, the electroscanning microscope, to observe the crack, right? The crack. Okay, therefore we can say, oh, there's an initial crack whose dimension, the half length of the crack is A. Okay, so you can compare with these two different factors, right? KT for notch, KI for crack. Okay, and we already know the KI is the stress intensity vector. Well, it's as related to the geometry of the crack, geometry and location. Okay, geometry and location of the crack. Okay, therefore, we're gonna multiply a vector. It's called the stress intensity modification vector. Okay, in front of the its original KI. So you will understand that this beta or y is represented as the geometric or location of this crack. Okay. Okay. And then as I mentioned, the stress, right? With the elements sigma x, sigma y, and tau x, y. And then we can just replace this term with the ki, right? We can replace this sigma times square root of the a over 2r. We can replace this with ki. Okay, so the sigma x will equals to this term. Okay, therefore there are two factors for the crack. First is the stress intensity vector and the stress intensity modification vector. Okay. Okay, so generally we define the crack based on some types. First is the crack as inside the component, Okay, and we assume this plate, this plate is the half infinitesimal mode. Okay, so well, the crack length is equals to 2a. And the second case is the crack length is along the surface. It's along the surface, and the A is defined as the crack length. Okay, that's why I say the stress modification vector define the location and the geometry of the cracks. Okay, so there's one example. Suppose we have the crack of the beam at the bottom surface, and this beam is subjecting to bending, right? The bending. Therefore, this stress will start to propagate right along this crack. Okay. And the third case is that if we design a hole of the plate, and after apply the stress, there's a small crack along this hole, right? Along this hole, and we can define this crack length is A. Okay, is A. And then right now we have to define the a material's property called fracture toughness. What is fracture toughness? It's the critical stress intensity vector KIC, or say the K1C. Okay, KI is for the crack, right? And the KIC is fracture toughness, which is a material's property, Therefore, okay, so if I say this material has the higher fracture toughness than that of the other, what's that mean? If the material has the higher fracture toughness, what's that physical mean? What's that physical meaning? Well, that's mean this material has the high resistance to crack propagation. That means suppose sorry, this component which has the high fracture toughness, when a small crack form inside or on the surface of this component, and it has the higher resistance to crack propagation. That means this material is not easy to trigger the crack propagation. Okay. Okay, so in general, this modification vector can be defined as the one if this crack is the internal crack, and this modification vector equals to 1.12 if the crack is along the surface. Okay, well, it's just a roughly define this modification vector. And the real modification vector has to look up the charts, okay? Different numerous charts to define these geometric vectors or the modification vectors. Okay, so what I mentioned is that the critical stress intensity vector KIC is the fracture toughness, which is the material's property. Therefore, you can check this value from any textbook, or you can Google it. Okay, so you can figure out, wow, so probably the steel has the average of the higher fracture toughness, right? Roughly, I'm not sure. And the titanium has the highest fracture toughness than the aluminum, or maybe higher than the steel. Okay. Well, this can be measured by the experimental design. Okay, it can be measured by the experimental design. Okay, so I'm gonna describe how a measure the fracture toughness here, but I just want to know the fracture toughness is the material's property. Okay. Okay, so this one example. Suppose the metal is operated at low temperature. Okay, therefore the ductile to brittle transition temperature might reach, right? So we can define the safety vector. Okay, we define, suppose we're gonna focus on the crack or the crack propagation. Okay, so we're afraid of whether this metal operating at low temperature, whether the crack will propagate or not. Okay, so in this case, we can define its safety vector by the KIC, the fracture toughness, and the stress intensity vector. Okay, so we say when this yielding stress divided by the ultimate stress, if this value is high, what's that mean? That means the small ability to observe energy, right? So suppose we work on the stress and strain curve, right? Or like this. Okay, so suppose this is the SY, and here is the SU, right? So when this unit stress is higher than the ultimate stress, ultimate, for example, is tension. Okay, so I'll say the ultimate tensile stress. When this value is high, that means they have this material has a small ability to absorb the energy. And the materials has the higher possible to brittle fracture, right? To brittle fracture. Okay, so suppose we're gonna focus on the ductile to brittle transition. So we can apply the safety vector by the fracture toughness divided by the stress intensity vector. Okay. Okay, so there's one example here. Okay, suppose we have a plate, okay, and there's an internal crack right here, and it's the load with 360 kilonewton, and the length of the crack is 90 millimeter. Okay, so what this factor of safety is, and what is the maximum force? And as we know, this titanium alloy whose fracture toughness, right, the material's property is 55. Okay, 55. Okay, so well, how do we work on this example? So the safety vector equals to KIC, that's the material's property, right? Right here. And the KI, okay? The stress intensity vector equals to beta times the sigma times the square root of the pi A, right? And the stress equals to the force divided by the cross section, right? So in this case, the force is the 360 kilonewton, and the area, the cross section, is the 0.3 times the 0.02 meter. Okay. And we get the stress equals to 60 megapascal. Okay. Okay, so this the megapascal, and then okay, so I already mentioned previously, if we want to exactly find the modification vector, the chart or table has to be looked up. Okay, if we just want to roughly, estimate the modification vector, well, we can say, well, it's an internal crack. Let's say the beta or y equals to 1. Okay. Okay, so okay, the B is 300 millimeter, right? Right, the width of the plate, the 2B. Let's say the 2B. Why we say the 2B? Because the chart shows here is 2B, right? And the B is 150, right? And the D, where's the D? It's the center. It's the center of the crack to the surface. Okay, the distance from the crack center to the surface. I mean the half of the width of the plate, right? Right. Therefore, it's equal to 150 millimeter. And the crack length 2A equals to 90 millimeter. Therefore, the A equals to 45. Okay, there are two important ratio we're gonna to figure out. One is the D over B, and the second one is the A over D. Okay, and then let's go back to this chart. D over B shows the different curve, A equals to 1, right? Therefore, this curve represents the ratio of D over B equals to 1. Okay, and the x-axis represents the ratio of the A over D equals to 0.3. supposed to here, right? Therefore, there's an interceptor right here, and then we can find the modification vector beta is around the 1.05, 1.05. Okay. So we say the beta equal to 1.05, right? Therefore, the Ki, the stress intensity vector equals to 23.7. Okay, here, and the materials property fraction toughness equals to 55, and we got the its safety vector equals to 2.32. And what is the maximum force? Maximum force will equals to the n, the safety vector, times the applied force, 360 kilonewton. Therefore, the maximum force equals to 835.2 kilonewton. Okay, so let's discuss about the crack propagation. So for this crack propagation, initially the crack has to be formed, right? And then it propagates. And then it propagates. Okay? Okay. So for the static loading, the issues we're gonna focus on is the stress, strain, right? The principal stress, and so on. However, for the cyclic loading, we have to take into account the concentration vector, right? Concentration vector and the failure and the crack issue. Okay, so this will cause the fatigue, right? The fatigue, which means the materials tired. Okay, materials tired. Okay, so this from the design, right? This is the groove here. This is from your design because you have some specific need, okay, for your design. You has to be design the groove. However, this groove design will cause the stress concentration. Okay. And the other case is the stamp mark. If you're gonna stamp your name or company name on your your surface of a component, and those mark, we can regard it as the crack on the surface. Okay, we can regard it as the crack on the surface. Okay, therefore the stress initially must start from the where the stress concentrated. Okay, therefore there's must have the nucleation point right here. The stress concentrated where the sigma max equals to K times the applied stress. Okay, and this maximum stress might be greater than the ultimate tensile stress or ultimate stress, or maybe just the yield stress. Well, right? And then the stress will start to propagate, right? Will start to propagate, and it will being processed in 3 stage. Okay, we'll be seeing 3 stage. Okay, so we have the initial crack, and then we'll see the beach mark, and then we'll see the remaining area. Okay, we'll see the remaining area. Okay, remaining area. Okay. So for no stress concentration, that's mean maybe this component just a polished shaft without any groove design, without any groove design or without any notch design, without any surface mark, without any surface mark. So it's a perfect polished shaft. Therefore, there's no stress concentration or with the very, very low stress concentration. Okay? Okay. And this high nominal stress, what's the cross section with the low stress or no stress concentration and the high nominal stress? Okay, so what I mentioned previously, we must have the stage one is a nucleate point, right? And the beach mark start to propagate, right? Cracks start to propagate. And then this remaining area is large compared to the beach mark area. If this component without stress concentration with the high nominal stress. Okay, so this the initiation point is the stage one, and this beach mark is stage two, and the remaining area is the stage three. Okay, and suppose this design with the severe stress concentration. That means this shaft may design with the V-shaped groove, V-shaped groove. Therefore, the nominal stress is low. Okay, the nominal stress is low because the remaining area is small. Okay, the remaining area is small. Okay, the force divided by area, when this remaining area is small, the nominal stress, sorry, yeah, we should say the low nominal stress applied to this severe stress concentration component. Okay. Okay, so this is a real case. You can look at the cross section of the initial point, initial crack point, and it's the change the color. It's the beach mark area, and the C is the remaining area. Okay, C is the remaining area. Okay, so this figure shows the already helps you to classify the different type of the fatigue and the fracture surface with the high nominal stress and the low nominal stress. Okay, and here for this first component, here's the component without any stress concentration with the mild stress concentration, severe stress concentration. And the same here, the component without any stress concentration with the mild concentration and with the severe stress concentration. Okay, so when this component without stress concentration is subjected to the high nominal stress, we can just cut through this cross section. We'll see the beach marks area and the remaining area. Okay, so for this this first, or say the second row, represent the unidirection bending. The unidirection bending. And so just bend it and release it, bend it and release it. Okay, bend it, release it, bend it, release it. Okay, so for this shaft with the low nominal stress, the sand is subjecting to the unidirection bending. And in this case, it will have the larger area of the beach mark and the small area of the remaining. Okay, and this is the second, and this is second chart of the my stress concentration. You will observe the ring outside. Okay, the ring outside here. Okay, and if this component is subjecting to reverse bending, That's mean this shaft is bending and reverse bending. Okay, it's bending and reverse bending. So we will observe the two region of the beach mark area of this cross section, right? This beach mark area, two beach mark area, and the center area is the remaining area. Okay, so anyway, you can just check those pictures by yourself. So when you work in a company or any machine design company and you observe the failure, you can evaluate and you can judge from its fracture surface to tell whether it's the high or low stress concentration or whether it's under, what kind of the stress applied to it. Okay. Okay, so there are some examples like this keyhole here, right? So we have the pin will be lock here. Will be a key will be insert to lock here. So there must be a stress concentration start from the location B, right? It's for sure because this is from your design. It's from your design. Okay, and finally, it fail breach line, right? So this remaining area is small right here. Okay. Okay, and there's some examples right here. Also, we design the hole, right? And there's a sharp corner right here, right? And we observe those pitch mark area and this remaining area right here. Okay. Okay, so how to evaluate the crack length and the stress cycle? I mean, how do we know how many cycles the crack length will grow or the crack will start to propagate? Okay. So we have to plot the figure of the crack length versus the stress number. Okay, stress number. Okay, so first we define the delta sigma equals to the maximum stress minus the minimum stress. Okay, therefore we can define the delta Ki, the delta of the stress intensity vector. Okay, right, and then we can define it as the delta K1 and delta K2 with two different crack lengths due to the delta sigma. Okay. Okay, and then we can plot this crack length, the figure of the crack length versus the stress based on experiment. Okay, based on experiment. So we can plot, I'll say, for example, for this component, we apply to the certain stress cycle, we get the crack length, right? And this point represents the initial crack. It's already there. It's already there, and this component is subjecting to the some number of cycles of the stress, and the crack will grow, right? Grows here, the crack will grow based on the number of cycle. Okay, and remember this x-axis, the units of x-axis represents by the log of the number of cycle. Okay, the stress cycle, number of the stress cycle. Okay, so the H curve of this on this figure caused by the different delta sigma, right? So in this case, it's a delta sigma. For this yellow curve, it's caused by the the delta sigma 1 and delta sigma 3, right? So for example, when this component is operated at the same number of cycle, right? And we'll find the different sorry, the different crack lengths. Okay, different crack lengths right here, here, and here. Okay, we'll find a different crack lengths, and then I can observe that the delta sigma 3 is greater than the delta sigma 2, is greater than delta sigma 1. Okay, it's delta sigma 2 here. Okay, and then we define the slope of this figure equals to the dA over dN. Right, it's a dA right here over dN, the slope, right? So we can define at any number of cycles, we can define this slope or this slope or this slope. Okay. Okay. And finally, the critical length defined as the AC, the critical crack length. That's mean here, here, and here. Okay, that's mean the crack start to propagate. Okay, we'll say the critical length, right? The cracks start to propagate. Okay, that causes the Ki equals to the K1C or equals to the KIC, which represents the fracture toughness, materials property. Okay, therefore we can find from this curve, we can know the crack grows by the different stress cycle. Okay, so the crack will keep growth, become bigger, bigger, bigger. And when this crack length reach the critical length, this crack will start to propagate. That's the situation I mentioned previously from stage 1 to stage 2 to stage 3. Okay. Okay, and then we can plot this curve. Right, we get the slope from the previous slide, right? And we take the log of the dA, the log of the slope, and the log of the delta Ki. Okay, and then we can just plot this curve represents the it will predict the fracture toughness. Okay, so this curve is also from the experiment, right? Because we operate the experiment to get the A over the N, the slope. Okay. Okay, so at this point, at this location, which represents the KIC, okay, the KIC. Okay, so we can assume this log relation is the linear. Okay, it's a linear relation, therefore we can assume this linear equation as the y equals to mx plus b, right? And y as the log of the slope, right? The x is the log of the delta Ki, right? M is the slope here, and the b is the intercept of the y-axis, right? Okay, so we can just operate it exponentially and run those mathematical process. Okay, so finally we got this equation, and uh, we can define this is the constant. Okay, we can define this as a constant. Okay, we can define this as the constant C. Okay, so it's by eliminating. Okay, so finally we got this relation between the slope from the previous slides. The dA over dN equals to the constant C times the delta Ki, the power of n, the power of n. Okay, so you can observe that the major region of this plot is the second one, right? So this is the linear, the second and the third one, right? It's a linear relation. Okay, it's a linear relation. So what's the use of this equation? We call it the Paris equation. Okay, the Paris equation. M is the slope, which is dimensionless, and C with the units, the SI units, and the English units. Okay, and then we can operate it by integration, right? You know what I'm saying? So we can just rearrange this Paris equation, right, to the end, just move to the right side. And this term just move to the left side as the denominator. Okay, so we got this equation. Okay, and we take the integration from the zero cycle to the final, or say the fracture cycle. Okay, the same we integrate from the initial crack to the final crack, or the fracture crack length. Okay, so we get a number of cycle of failure or fracture. Right, so we can evaluate if this component, which already has the crack inside or on the surface of the components. Okay, and then we can evaluate how many cycles, after how many stress cycles, this component is gonna fail. Okay, it's gonna fail. Okay. Okay, so let's finish this example. We have the beam here, and there's a small crack here. Okay, so this is the L, the whole length is L. So the crack is located at the 1/3 of the whole length. Okay, and this beam or this rod is made by steel, and the KIC is 68. C, the constant, equals to 3.8 times 10 to power of minus 11, and M equals to 3. It's by experiment. Okay, it's the dimension. And the question is how many cycles, stress cycles, it's gonna fail. That means we press the force 250 pounds, and we release the cycle. We release the stress. We release the force. Okay, we press 250 pounds and release, and press 250 again and release. And we're just repeating this the loading cycle, and how many cycles they're gonna fail. Okay. Okay, so I just quickly okay. So we have to figure out the first that we can find the maximum bending stress, right? Because this shaft or this rod is subjected to the bending, right? Subject to bending. So, and this force is applied to the center of the rod, right? So we know the reaction force of each support is half of F, right? And then we can plot the shear and bending moment diagram. From this shear and bending moment diagram, we can find the maximum normal stress. Maximum normal stress here. Okay. And again, we have to check the table or chart. Okay, and the initial, the crack length is the 0.006 inch. The D equals to 0.4. Okay, 0.4. And the R radius equal to 0.2. Okay, and A over R equals to 0.03. So because in this case it's a solid rod, therefore uh the internal radius equal to 0, right? Okay, so the A over R ratio equals to 0.3. Okay, and the Ri over Ro equals to 0, right? Because the internal radius equal to 0. So, well, it's probably here. Okay, so the beta, the modification vector is about 1. Okay, it's about 1. Okay, so modification vectors about 1, the AF, the final crack length or the fracture crack length. Okay, so we can define the fracture toughness, right? When this Ki equals to KIC, that's mean the crack start to propagate, right? Which is equals to the modification vector times the delta sigma times the square root of the pi AF, right? And then we can just rearrange this term, right? Because the KIC is the materials property, right? And the steel is about 68. And we can rearrange this equation to figure out what's this final crack length or fracture crack length. It's a 0.232 inch. Okay. And the number of cycle, well, from this Paris equation, right? I have to take the integration from the initial crack to the final crack. Where's the final crack? Here. Right? And we know the beta, delta, sigma, and the crack length, right? And then we can just work on this integration. And finally, we plug those number, right? And we take the integration from the initial crack length to the final crack length. Okay, so we got the number of cycles to the number of distress cycles to cause this solid rod fail. Okay, so next I'm gonna introduce the SN diagram. Of course, it's also from the experiment. It's the stress and the number of cycle diagram from the experiment, and we can just evaluate the fatigue strength corresponding to number of cycles. And also the very important parameter is called endurance limits. Okay, so we are gonna introduce next time. Okay, so we are gonna stop here.